Giant steel cables are some of the strongest flexible structures ever engineered, quietly holding up suspension bridges, lifting skyscraper components, anchoring offshore platforms, hauling elevators hundreds of meters into the sky, and carrying loads so massive that solid steel bars would snap under the same stress. Yet behind each cable is a highly controlled industrial process that begins with molten steel and ends with precisely stranded, tension-balanced wire systems designed to survive decades of constant load, vibration, weather, and fatigue. What looks like a simple twisted rope of metal is actually a carefully engineered composite of thousands of steel filaments, each one heat-treated, coated, aligned, and tensioned, so the final cable behaves as a single ultra-strong unit. And today on the How Factory, we're going inside modern steel cable plants to see exactly how giant steel cables are made, from molten steel to mega-strength lifelines used around the world. The story of steel cable begins in the 19th century, when industrialization demanded stronger lifting and suspension systems than hemp rope or chains could provide. Early wire ropes revolutionized mining, bridges, and elevators by combining strength with flexibility. Over time, metallurgy improved, steel purity increased, and wire drawing technology advanced, allowing cables to grow stronger, longer, and more reliable. Modern steel cables are no longer simple ropes. They are precision-engineered load systems, built to exact standards depending on whether they will support a bridge deck, lift cargo, or stabilize massive structures. The process starts at a steel mill. Steel used for cable production is typically high-carbon steel, chosen for its ability to achieve very high tensile strength after heat treatment. Raw materials such as iron ore, coke, and limestone are melted in blast furnaces, producing molten iron, which is then refined into steel. Alloying elements may be added to control strength, toughness, and fatigue resistance. The molten steel is continuously cast into billets or rods, which are solidified and cut into manageable lengths. These steel rods are not yet suitable for cable use. They must first be transformed into wire. The rods are reheated and rolled into thinner rods, then cleaned to remove surface scale. Cleaning often involves acid pickling, which strips away oxides and leaves a clean steel surface. After rinsing and drying, the rods are ready for wire drawing, one of the most critical stages in cable manufacturing. Wire drawing begins by pulling the steel rod through a series of progressively smaller dies made from tungsten carbide or industrial diamond. Each die reduces the diameter slightly, elongating the steel and increasing its strength. Drawing aligns the steel's internal grain structure, which is key to tensile performance. This process happens in multiple stages, sometimes reducing rod diameter by more than 90%. Drawing generates heat and internal stress, so the process is carefully controlled to prevent cracking or brittleness. As the wire becomes thinner, it is periodically heat-treated. Heat treatment, often in continuous furnaces, relieves internal stresses and restores ductility while preserving strength. For high-performance cables, steel wire may undergo patenting, a specialized heat treatment that produces a fine, uniform microstructure, ideal for drawing and fatigue resistance. The balance between hardness and flexibility at this stage determines how well the final cable will perform under cyclic loads. Once drawn to final diameter, the wire is inspected for surface defects, diameter consistency, and tensile strength. Even microscopic flaws can become failure points when thousands of wires share load, so quality standards are strict. The wire is then coated to protect it from corrosion. Galvanizing is the most common method, where wire passes through molten zinc, forming a protective layer that resists rust. Some applications use specialized coatings or stainless alloys depending on environment. Now, the process shifts from wire production to cable construction. Individual steel wires are wound onto large spools and transported to stranding lines. Stranding is where thousands of individual wires are transformed into a single cable. The first step is creating strands. Multiple wires are twisted together in precise patterns to form a strand. The twist direction, pitch length, and tension are all carefully controlled. If tension is uneven, some wires will carry more load than others, reducing cable life. Strands themselves can vary in design. Some use a simple configuration with a central wire surrounded by layers, while others use more complex geometries that improve flexibility or fatigue resistance. Once strands are formed, they may be compacted slightly to reduce voids and improve load sharing. Next comes closing, where multiple strands are twisted together around a core to form the full cable. The core may be steel, fiber, or synthetic material depending on application. Steel cores add strength and temperature resistance, while fiber cores improve flexibility and lubrication retention. For giant structural cables, steel cores are common because maximum strength and stability are required. Closing machines are massive. Large rotating frames hold spools of strands and twist them together under carefully controlled tension. The process can take hours or days for very large cables. Sensors monitor tension continuously to ensure every strand shares the load evenly. Lubricants may be applied during closing to reduce internal friction and protect against wear as strands move slightly under load during service. For extremely large cables, such as those used in suspension bridges, the process may involve parallel wire construction rather than traditional rope closing. In these systems, individual wires are laid side by side under tension and bound together, creating cables that can contain tens of thousands of wires. This method allows engineers to control tension in each wire individually, achieving unmatched load capacity. Once the cable is formed, it undergoes compaction and finishing. Compaction presses strands together to reduce diameter and increase contact between wires, improving strength and reducing stretch. The outer surface may be smoothed or shaped depending on specifications. Some cables receive additional protective layers such as plastic sheathing or grease-filled jackets to shield them from moisture and chemicals. Testing is one of the most important phases. Finished cables are subjected to rigorous mechanical testing. Tensile tests pull sample lengths to destruction to verify breaking strength. Fatigue tests simulate millions of load cycles to ensure long-term durability. Bending tests confirm flexibility. Non-destructive inspections check internal structure using magnetic or ultrasonic methods. For safety-critical applications like bridges and elevators, testing standards are extreme. Length control is another challenge. Giant steel cables are often produced in continuous lengths, measuring hundreds or even thousands of meters. Precision measuring systems track length during production. Finished cables are wound onto enormous drums that can weigh dozens of tons. Handling these drums requires cranes, reinforced floors, and specialized transport equipment. Different applications demand different cable designs. Elevator cables must balance strength with flexibility and smooth operation. Crane cables prioritize abrasion resistance and fatigue life. Bridge cables focus on ultimate tensile strength and corrosion protection. Offshore cables must resist salt water, pressure, and constant motion. Manufacturers tailor wire diameter, strand count, core type, and coatings to each use case. Sustainability also plays a role. Steel cable production is energy-intensive, but steel is highly recyclable. Scrap wire and end-of-life cables can be melted down and reused without losing strength. Modern plants optimize drawing efficiency, recover heat from furnaces, and reduce coating waste to lower environmental impact. What makes giant steel cable manufacturing remarkable is how it turns brittle raw steel into something flexible yet incredibly strong. No single wire carries the load alone. Strength comes from numbers, alignment, and precision. If just one stage is poorly controlled, drawing, heat treatment, stranding, or tensioning, the entire cable's performance is compromised. From molten steel poured in mills to rods drawn thinner and stronger, from thousands of wires twisted into strands to massive cables wound onto drums. The journey of a steel cable is one of the most impressive examples of industrial engineering working at scale. And that is how giant steel cables are drawn, heat-treated, coated, stranded, closed, tested, and delivered, transforming molten steel into mega-strength lifelines that hold up cities, move mountains, and keep the modern world connected. Thanks for watching The How Factory.